Hi everyone, in this video we're going to start off a very special lecture series on real analysis beginning with the theory of sequences, talking about convergence and the rigorous epsilon-delta definition of convergence of sequences, all from the basics very intuitively. And my name is Amitesh and I'm a research mathematician and I've received a PhD in math at Princeton University, also received a faculty teaching award teaching math at Princeton University after receiving my PhD, and I actually taught myself this stuff when I was 12 years old, so I have a lot of experience with advanced math and advanced math thinking, and I'm going to deliver to you all the insights I have in this video on the theory of sequences. So let's just dive right into it. What is a sequence going to be? So first of all, we start off with the basics and just build up from there very rigorously. So definition is a sequence. So what is a sequence? A sequence is an infinite tuple of numbers basically. So a sequence is an where n is at least 1. This is a sequence. We also denote it by a1, a2, a3, dot dot dot, an, dot dot dot, where these are numbers. Okay, so it's a sequence of numbers. Each one, a1 is the first number, a2 is the second number, a3 is the third number, etc. And an for n at least 1, this is how we also denote the sequence. And to give you some examples, because this is all very rigorous or very formal, is you can sort of take like something like 2, 1, 1, 1, dot dot dot. This is an example of a sequence. You know, just maybe you could say it starts off at 2, then it becomes 1, 1, 1, 1. That's a sequence. You could also have a sequence that starts off like this, 0, 1, 0, 1, dot dot dot. So just kind of swaps between 0 and 1. You could also give sequences as formulas in n. So for example, you could write a sequence like this, 1 over n, n at least 1. So this sequence is just all the numbers of the form 1 over n as n goes from 1 to infinity. So it starts off at 1, then it becomes half, then it becomes 1/3, then it becomes 1/4, etc. That's going to be a sequence. You could also have another sequence that looks like this, which is -1 to the n. Okay, so this sequence, you could say as n at least 1. So we could write it like this. This is just a sequence which alternates. So if n is 1, it's -1. If n is 2, it's +1. So it becomes -1, +1, dot, 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 just alternating. Okay, so these are all examples of sequences. And the primary thing we're interested in when we study sequences in math, one of the things we're interested in is whether they converge or not. Okay, so what that means exactly, I'm going to talk in detail and make a rigorous math definition. Okay, so if you kind of know of the epsilon-delta definition of limits or of sequences, this is going to be very motivating for where that comes from and how we think about it. So we know what a sequence is. It's just an infinite tuple of numbers. The next step is to define convergence. So let's kind of get into that. So the way we like to think about convergence is, does the sequence approach something? Okay, that's the fundamental question. As we take the terms in the sequence, does it eventually approach some number? And the basic example that we have over there, or one example that's good, is the 1 over n when n is at least 1. Okay, so this is the sequence 1, half, 1/3, etc. Does this eventually approach something as n goes to infinity, so to speak? So as we take 1, half, 1/3, 1/4, 1/5, etc., the numbers get smaller and smaller, and eventually they will get closer and closer to 0, right? That's the intuition. And so in that sense, we kind of want to say, if you don't know calculus, it's totally fine. You can still understand all this. But limit n goes to infinity, this is the notation of 1 over n is equal to 0. So here when we say limit, we're just going to say that as n gets larger and larger, that's what it means, n goes to infinity, this 1 over n, which is the nth term in the sequence, becomes smaller and smaller, eventually gets really close to 0. It never reaches 0, but it gets as close as you like to 0. Okay, so even if you know calculus, I'm rephrasing this because we need to think very precisely about what we're trying to do. And the next step is to be very mathematically rigorous on how we can formally define this idea of closeness. Because saying that, oh, it just gets closer and closer to 0, that's too colloquial. For the liking of math, that's too colloquial, because then you don't know what your foundations are. You have to be rigorous. So here's another way of looking at it. If you sort of take your point 0, you can sort of imagine the number line. It doesn't matter how far in you zoom into 0, whatever scale you're looking at. Eventually, the terms of the sequence will get within that scale. Okay, so imagine this is a really zoomed in. Okay, so I haven't told you the endpoints of this interval somehow. So maybe, suppose we've zoomed in and this interval is like -1 over, 1 million. Okay, and this is +1 over 1 million. It doesn't matter. There is going to be some point of the sequence where it eventually is going to be within this range. Okay, so in this case, if you take the terms of the sequence that are the millionth and first and beyond. Okay, so if you look at 1 over n, for n at least 10 power 6 plus 1. Okay, so 10 power 6 is a million, then you know that the 1 over n is going to be very close to 0. And how do we precisely mean close to 0? Well, we think about distances. So what is the distance from 1 over n to 0? Well, it's not the difference, because the difference could be negative. In this case, it's not negative if we take 1 over n minus 0. But in general, the distance between two numbers should be a non-negative number, so we use the absolute value. So say the absolute value of 1 over n minus 0 is going to be, for n at least 10 to the 6 plus 1, this is going to be less than 1 over 10 to the 6. Okay, so that means that it's going to be in this range of 0, okay, in this interval 0. In this example, our sequence is approaching 0 from the right, but even if it was approaching 0 sometimes on the left, okay, that's totally okay as long as it's getting really close, which means it's within this range of 0. So here we found that no matter how small we made the distance that we wanted, in this case 1 over 10 to the 6, which specified this interval containing 0, we could eventually ensure that late enough terms in the sequence are all going to be in that interval, which is to say the absolute value of 1 over n is less than 1 over 10 to the 6. Okay, so that's what we are kind of thinking about when we think about this idea of a limit, is no matter how small you prescribe, how much you zoom in, or how small an interval you prescribe, you can always get in that interval eventually. Okay, so that's going to be the idea, and we need to be very careful about how we think about this as well, because it's also important to realize that in this kind of situation, what matters is not what happens in the sequence early on, but eventually what happens. Okay, so even if the terms of the sequence initially do some crazy and wild things, right? Even if the sequence starts off with something like, 10 to the 6, then 10 to the 9, then 10 to the 6, and suppose it keeps on doing this for 1 trillion steps, okay? It doesn't matter. It keeps on doing this for 1 trillion steps, but then it corrects its behavior. Okay, so then it starts becoming 1/2, 1/3, 1/4, etc. We would still say that this sequence eventually converges to 0, so to speak. It eventually approaches 0. Now, it's also okay if after 1/3 it did something crazy again, as long as it doesn't do that. Okay, as long as there is a point where it stops doing that, that's totally okay. Okay, so on the other hand, here's an important example, so I'll erase this. If we had a sequence like the following, so I'm just going to kind of state this example, which I think is illustrative, is that if you had a sequence like the following, which was like, 1, 1, half, 1, 1/3, 1, keep on going, 1/4, 1, etc. So you sort of see that half the terms are kind of going towards 0. They are the usual sequence we just saw, but the other half of the terms are 1s. That won't do, because there's no kind of point of the sequence where beyond that point it's always within as close of a range of 0 as you want. Okay, there is no such point. So this sequence doesn't have a limit that's equal to 0. So all in all, what we want to say is, this is going to be the following definition. I'm going to state it very precisely now. It's going to be the definition of convergence. So the definition of convergence is going to state, it's what's called the Epsilon-Delta definition. Okay, so it's kind of like a very rigorous definition. It's very common even in calculus. You can define it for limits like this. You may have seen that, but we're going to just do it from scratch here. So what the definition is, it's going to be the following, is we say that, so here's the definition, we say that a sequence, so I'm just going to write this way, a sequence an, where n is at least 1, converges, okay, so this is a definition, converges to A, where A is some number, okay, so we don't know what the number is, it converges to A if the following is satisfied, okay, so if for each epsilon greater than 0, so now epsilon is a Greek letter, okay, just denotes some number greater than 0, it can be small, okay, the idea is conceptually it's small, for each epsilon greater than 0, there is an n, which is a big N, okay, I'm denoting it by big N, such that the absolute value of an minus a is less than epsilon for all n at least n, big N. Okay, so what this means is that no matter what epsilon you pick, which is some degree of specificity of around the point A, so here the sequence is converging to A, so we're saying that you take A and you take some small interval containing A. which goes from a minus epsilon to a plus epsilon. Okay, so being in that interval means that, so what does it mean to say that an is in the interval? It means to say the absolute value of an minus a is less than epsilon, right? That means the absolute value is, it could be on the left of a, on the right of a, as long as it's within epsilon, a distance of a. So as long as for each epsilon there is an n, so that beyond that term, beyond that n, all the terms in the sequence are in that interval, then we say that the sequence converges to a. Okay, so that's going to be the definition of convergence. And so you can prove, now with this definition, you can rigorously prove what the limits of certain sequences are. So I'm going to do, another video. I'm going to talk about all the limit laws, why the sum of the limit is a limit of the sums, why the product of the limits is a limit of the product, rigorously from this epsilon definition. Okay, but in this video, I'm just going to show you one or two examples of such a thing just to warm you up. Okay, so let's kind of dive into that. So let's talk about two examples of such a thing, which I think are pretty important, and the examples are going to be the following. Okay, so let me erase this. So I will now use this marker. So I'll just erase this here. So we're going to talk about the following sequences. So we talked about the sequence 1 over n. We sort of convinced ourselves it converges. Let's talk about another sequence and kind of make it a little bit interesting. Let's talk about a sequence like, let's say, 20 over n. Okay, 20n over n plus 1. Okay, 20n over n plus 1. Just a random sequence I came up with. Okay, 20n over n plus 1, n is at least 1. So this sequence, does it have a limit? Does it converge? What does it converge to? Okay, that's the question. Now, the point to observe is first, of course, you have to prove, you have to guess, what the limit would be. And then you can rigorously prove this condition is satisfied. Okay, so first we have to guess, we have to use our intuition. So what does our intuition tell us? Well, if we think about n over n plus 1, then as n gets larger and larger, n over n plus 1 gets closer and closer to 1. 10 over 11, pretty close to 1. 100 over 101, very close to 1. 1 billion over 1 billion and 1 is basically starts becoming 1 almost. Okay, so it never reaches 1, but it's pretty close to 1. And so if you multiply that by 20, you expect that something that's approaching 1, you multiply by 20, you expect it should approach 20, right? 20 times 1. So that's going to be a limit law that you can actually rigorously establish. But let's sort of kind of rigorously prove this, that this limit is 20. Okay, so here's a theorem. So let's say it's called a lemma. Okay, that limit as n goes to infinity of 20n over n plus 1 is equal to 20. Okay, so how are we going to prove this? We have to use the epsilon n definition. We have to show that no matter how close you want to get to 20, you can eventually get that close with terms of the sequence. So this is going to be the thought process of how you actually do that. Okay, so that's, I can tell you, if I give you an epsilon, you have to give me an n in terms of epsilon. It's going to depend on epsilon because epsilon gets smaller, your n is going to have to get larger. So that beyond that point in the sequence, your sequence is within epsilon of what your limit is. But how do you even find the n? What's the process? So that's what we're going to do right now. We're going to talk about the process of finding the n. So we're going to work backwards and then construct the proof. So I'm going to show you the thinking process. Okay, so the way we're going to do it is as follows, is we're going to say that, okay, we think it should be 20. Okay, so suppose we want to ensure that 20n over n plus 1 minus 20 is less than epsilon, right? What condition do we need on little n to ensure that? Okay, we're going to work backwards and then we're going to prove that that condition suffices. So here, how do we do this? Well, let's take the difference. Okay, let's make a common denominator. So we want to basically say 20n minus 20 times n plus 1 divided by n plus 1. Okay, that's the absolute value. This is what we want to be less than epsilon. But let's kind of simplify it. Well, it's going to be 20n minus 20n minus 20, right? So it's going to be minus 20 divided by n plus 1, which is going to equal to 20 divided by n plus 1. Okay, so absolute value of minus 20 is plus 20, so it's going to be 20 over n plus 1. And now what we can do is we want to say that this is less than epsilon, right? That's what we want. So how do we solve for n? What should n be so this is less than epsilon? Well, everything is positive, so let's multiply the inequality through by n plus 1. So this is the same as saying that 20 over epsilon is less than n plus 1, which is the same as saying that if you subtract 1 from both sides, n is greater than 20 over epsilon minus 1. So let's think about this. if epsilon is a very small number, 20 over epsilon is going to be very big, right? If you think epsilon is really, really small, 20 over that is going to be huge. Subtract 1 is still going to be huge. So if epsilon is small, you found this 20 over epsilon minus 1. So you're saying that as soon as you go beyond that point, your terms in the sequence are going to be within epsilon of 20. That's the idea. So you kind of proving the definition. You know, you're proving, using the definition, you're saying that if you take that n, for each epsilon you have an n, so n at least n implies this term of the nth term of the sequence minus 20 has absolute value less than epsilon. So 20 over epsilon minus 1. So let's now prove it. Okay, let's now rigorously prove it. So that's the thinking process. Now let's write the mathematical proof. And the mathematical proof is not going to use, you know, any kind of backtracking. It's going to be very rigorous. It's going to show that that limit is 20. So how does that work? So what we're going to do is the following. Here's the proof. So the proof is that let epsilon greater than 0, choose n. So we're going to choose n is equal to 20 over epsilon minus 1, right? That's what we're going to choose n is. So if n is greater than, if little n is greater than big N, now in the definition I said n is at least big N, but it's the same idea, okay? Otherwise you can just adjust big N by 1 to get the same equivalent definition. But if little n is greater than big N, then you know that you want to say the nth term of the sequence, which is an, right, which is 20n over n plus 1 minus 20. So if you want to think about our definition that we had, this was the nth term of our sequence, this was an, and this was a, right? So we want to estimate, we want to say that distance is small, so those two terms are going to be very close. So what we do is we say, okay, this is, do the same process basically, it's just backtracking. 20n minus 20n plus 1 divided by n plus 1, which we know is going to be absolute value of minus 20 over n plus 1, which is going to equal to 20 over n plus 1. Okay, and since we know that n is bigger than, little n is greater than big N, right? We know that, so I'm going to do it on this side of the board. We're given that when n is beyond that point, we want to say this is less than epsilon. So if n is bigger than big N, which we know is 20 over epsilon minus 1, then that implies that n plus 1 is going to be bigger than 20 over epsilon, right? And now, using fractions, if n plus 1 is bigger than 20 over epsilon, if you take reciprocals, you know 1 over n plus 1 is going to be smaller than 1 over 20 over epsilon. But 1 over 20 over epsilon is just epsilon over 20. Okay, so that means that therefore 20 over n plus 1 is going to be less than 20 times epsilon over 20. Okay, because 20 times 1 over n plus 1, so that's going to be equal to epsilon. So therefore you know that the distance between the nth term of the sequence and its limit that we claim it to be, which is 20, that distance is less than epsilon whenever little n is bigger than big N, and that proves, okay, so that's the proof that therefore the sequence converges and its limit is equal to 20. Okay, so this is how you rigorously prove these things. It's not, you know, once you kind of learn the laws, you can apply the laws like you do in calculus. You know, if you've seen calculus, you can apply the limit laws and calculate these things. But the point of doing this rigorously is to train you in mathematical thinking, to sort of say this is what it really means for the limit to be what it is, and then to prove it that way. So in a future video, I'm going to go through the steps of real analysis, prove statements rigorously, show you how to think about them. I hope you love this video. You know, remember, before you click away, I just wanted to say I'm creating elite math education. I'm so happy you're watching this video because I'm trying to create elite math education at all levels. You know, my channel has math from very basic math that anyone can understand without any background to very advanced math, you know, like proof-based math, for example. I'm building a library at all levels to help as many people as possible. So no matter where they are, what college or high school they're going to, they can have elite math education delivered right to them. And ultimately, with the resources I have, as I keep building my channel and growing my resources, I want to help underprivileged people who may not even have internet access, try to give them internet access, help support them. Because I think that math education and any education in general is really powerful. Everyone should have access to it. We're living in the 21st century. And, you know, by creating this channel on YouTube, I'm taking the steps towards achieving that goal and vision of mine by watching, liking, subscribing, and spreading the word to everyone you know, whoever, you know, whatever level of math they're doing, there's going to be something on my channel for them. So if you spread the word, that would really mean a lot to me to help achieve my goal of helping as many people as possible. But just by watching, you've already supported me a lot, and I'm super excited to see you in the next video. Wish you all the best. I hope I was able to support you. You enjoyed that content, and I'm super excited to see you in the next video. Please take care, and I will see you soon.